Hello everyone, welcome to this 9th video on power spectral density. This video will explore on linear system with random inputs. So we will see first what is meant by linear system with random inputs, and then what are going to be the quantities we will be requiring to compute the output power spectral using the input power spectral using the power transfer function. And then we will try to explore important theorem which connects the input and the output power spectral density using the system transfer function or the power transfer function. So now we will begin with linear system with random input. Say suppose first we will have to define what is meant by a system. If you are going to give an input, and if this input is going to be processed and then it provides you with an output, then such an setup is referred as a system. A system is one which takes an input, processes and gives you an output. Now if I am going to denote this input by x and the process be any function called as f and the output by y, then I can say that my output y can be expressed as a function of the input x. So this is how I define a system. Now if this input is going to be a power spectral density, then I will have it as Sxx, and in which case it is going to be processed. What will it produce? It will again produce an power spectral density. And how will this output power spectral density be denoted as? It will be denoted as Syy. So if you are going to provide the system with Sxx, what does it provides you back with? It provides you back with Syy. How does it do? It processes the input and then it provides you the output. So this processing function can be different for each different system. And now coming to the random part. If the input is not going to be deterministic in nature, that is not, you are not able to say this is going to be at a t equal to 1 second this will be my input, at t equal to 2 seconds this will be my input, but the input keeps on changing. It is not going to be deterministic but it is going to be probabilistic in nature, then you call it with a system with a random input. Now coming to the part of linear, why do you call a function to be linear? Whenever you have f of a1 x1 of t plus a2 x2 of t to be defined as a1 f of x1 of t plus a2 f of x2 of t. If the expression of this function as a split function of this part is going to be possible, then you call the system to be linear. So for linearity you have the function of a1 x1 of t. A1 and a2 are going to be constants over here. x1 of t and x2 of t are going to be my inputs. Then if my output process can be written as a sum of the independent input processes, then you call it to be the system as a linear system. Now moving on, the output process which is going to be y of t can be expressed as the convolution of the input process x of t. How can this be done? By the help of a system weighing function. The system weighing function is also referred by the name unit impulse response, and it is denoted by the script called as h of t. That is, my capital Y of t, the output, can be expressed as the convolution. This asterisk mark stands for convolution. Convolution of unit impulse response h of t, convolution the input process your x of t. Now how is this h of t important to us? This is important in defining an important quantity called as system transfer function. What is the system transfer function? You define this system transfer function to be the format h of omega, which is the Fourier transform of my unit impulse response. So for this unit impulse response h of t, if I am going to take the Fourier of it, f, then you call it to be a system transfer function. Why is this and now how I can refine the Fourier as integral from minus infinity to infinity? Your input is here. Since it is positive Fourier, you have a negative sign over here, in which way you can remember the formula and so on. So in how this system transfer function is going to help us, now as we saw in the block diagram, you have an input, there is going to be a processor, and then it processes and gives you an output. So I have an SXX, I need, or I will be getting an SYY. What is going to be processed over here is the one which we refer by h of omega. So what do we do is, I have an SXX, I have it to be processed with h of omega, and I get this as my output SYY. Now this format of the input process output can be defined by means of a theorem which is going to be of practical importance to us, which is given by Sy of omega is modulus of h of omega the whole square into Sxx of omega. So the output can be expressed as the product of the input and the system transfer functions modulus the whole square. So when you are doing this, is going to be the process. So the process into the input is going to give you the output. So this is going to be one formula we are going to memorize and then apply it to our problems, which is going to be of part C problems. So moving directly to the problem, we have a WSS process x of t is the input to a linear system with impulse response h of t, which is given by 2 e power minus 7t into u of t, where u of t is the unit step function, and the autocorrelation function is provided as rxx of tau is e power minus 4 times mod tau. We will have to find the power spectral density of the output process y of t. So as such, what we want is the power spectral density S. So of what? Y. So I want SYY. So I am determined in finding SYY of omega. And my SYY of omega depends on two quantities now. What are they? One is going to be h of t and the other one is going to be my autocorrelation function. So what do I know about connecting all these three components? I know that Syy of omega is modulus of h of omega the whole square into Sxx of omega. So there are going to be two components which is going to be required over here. One is going to be h of omega, which can be got from our h of t. The other one is going to be Sxx of omega, which can be got from our Rxx of tau. So we will move on step by step. The first step or step 1 is to pen down the formula. Okay, so first have the habit of writing the formula. Syy of omega is mod h of omega the whole square into Sxx of omega. Now our step 2. What is our step 2? Let me compute what is going to be my h of omega. So we will see h of omega as the Fourier of f of t. So I know that h of omega is integral from minus infinity to infinity h of t e power minus I omega t into dt. Now this limit extends from minus infinity to infinity. But what happens for the case for me? I have my h of t to be defined as my h of t is 2 e power minus 7t into u of t. What is this u of t? This u of t is going to be unit step function. What is the speciality of this unit step function? This unit step function is going to take the value of 1 for t greater than or equal to 0 and 0 elsewhere. So when our t is going to be greater than or equal to 1, this value over here becomes equal to 1. So obviously my h of t, unit impulse response, will now become 2 e power minus 7t times of 1. When will this happen? Whenever I have t to be greater than or equal to 0. What happens in the other case? This will be multiplied with 0 and so the entire function vanishes. So I now consider this limit for my integration for t greater than or equal to 0. So I have this as integral from t varying from 0 to infinity h of t, which is the input. What is the input? 2 e power minus 7t, and then you have in the formula e power minus I omega t, and then this has to be integrated with respect to dt. We need to keep in mind or recollect the hints which we have learned from video number 1 to 4. So whenever the base is going to be exponential, then we can club them easily as, so 2 constant 0 to infinity e to the power of, so let me club this as e power a into e power b is e power a plus b. So this becomes minus 7t minus I omega t into dt. So this is my rule or hint number 1. Hint number 2. Whenever I have infinity as my limit over here, then I will have to keep minus sign outside my exponential so that e power minus infinity turns out as 0. So following this hint, what do I do is I take this minus sign outside, so leaving me with 7 I omega times t. This has to be negative, hence this has to be positive. So minus 7t minus I omega t into dt. So this is my quantity. Now let me integrate it. E power a theta on integration is e power a theta divided by a. So this gives me e power minus 7 plus I omega times t divided by minus 7 plus I omega. Now apply it between the limits 0 to infinity. When your t takes the upper limit infinity, what will happen? You have a minus sign here, so it becomes minus infinity. What do you know about e power minus infinity? So e power minus infinity will move towards 0. So there will be no upper limit for us. There will be only a lower limit that exists. And about the lower limit, now t takes the lower limit to be 0. What is e to the power of 0? E power 0 makes it as 1. So what you will have is 2 times of upper limit is 0 minus lower limit e power 0 makes it as 1 divided by minus 7 plus I omega. So now this gives me minus sign cancels off, so leaving you with 7 plus I omega. So what we have for h of omega is going to be equal to, my h of omega is going to be equal to 2 by 7 plus I omega. Now my step 3. What I want is modulus of h of omega the whole square. Refer to your formula, modulus of h of omega the whole square. H of omega has been got. So now I need to take the modulus of it. So whenever I have a complex number a plus ib, the modulus of the complex number is given as root over a square plus b square, that is real part square plus imaginary part square. So what will happen over here? I am going to take modulus of h of omega as 2 divided by 7 plus I omega. Modulus of a real number is going to be the same real number. Real number doesn't get changed by the modulus, so it becomes 2. And what about the denominator? It becomes modulus of 7 plus I omega, which is a complex number. So I will have this as root over real part square, so it is 7 square plus imaginary part square. Imaginary part square is omega square. Keep in mind, whenever you say imaginary part, it is the quantity attached with I. Don't take this I, square it and write this as minus sign. That is a mistake. So keep in mind, caution, don't take your I. Imaginary part is the element attached with I. So you will have just omega square over here, not I square. Don't take an I square and make this plus as minus sign. Now the next step is h of omega the whole square. Whole square is there. So you have to square this data. When you square this data, what will happen? 2 square will make it as 4 divided by root over will the whole square. Root and square cancels off, leaving you with 7 square plus omega square. So that becomes 4 divided by 49 plus omega square. So my step 3 is over. Now moving on, I will have step 4. What is going to be my step 4? I want to compute the second part of the relationship. What is it? Sxx of omega. So I will have to compute Sxx of omega using my Rxx of tau. So what is the relationship that connects my Sxx of omega with Rxx of tau? Here I recollect the formula. Sxx of omega is minus infinity to infinity Rxx of tau e power minus I omega tau mod tau. Okay, because I know that my Sxx of omega is going to be equal to Fourier of your Rxx of tau. So the Fourier formula is Rxx of tau e power minus I omega tau d tau. Now take the input minus infinity to infinity. What has been given as your Rxx of tau? E power minus 4 times modulus of tau. So this has been given to us as input e power minus 4 times modulus of tau. So now this has to be multiplied with e power minus I omega tau into d tau. Now this is going to be exponential, this is going to be exponential, so I can club both of them. Minus infinity to infinity e power minus 4 into modulus of tau minus I omega tau d tau. This is using my hint number 1. Whenever base is going to be e, you can club them. Now coming to my second hint, the second hint is that whenever we have modulus over here, the interval minus infinity to infinity cannot behave the same, tau does not behave the same in both minus infinity to infinity. What happens? Modulus tau in the interval minus infinity to infinity, between this minus infinity to 0 it is going to be negative, and 0 to infinity it is going to be positive. So the idea or the hint given to us was split this into minus infinity to 0 e power minus 4 into modulus of tau minus I omega tau d tau, plus the second limit 0 to infinity e power minus 4 into modulus of tau minus I omega tau d tau. So hint number 1, base same, club them. Hint number 2, when you have modulus minus infinity to be split as 2 portions and then done. Now what we know about this quantity, tau is going to be negative in this zone. So what happens over here in this zone, tau has to be replaced as minus tau. So this tau will be replaced as minus tau. Now in the second zone, between 0 to infinity, tau is going to behave in a positive manner. So what will happen? My tau over here, modulus of tau will be replaced as positive tau over here. So minus of minus makes it as plus, minus of this plus makes it as minus. So we can rewrite our statement in the next page as integral minus infinity to 0 e power minus 4 into minus tau, because tau is going to take negative value, minus I omega tau d tau. Okay, so this is going to be my first part. Second part is plus 0 to infinity e power minus 4, tau becomes positive, minus I omega tau d tau. So this is going to be my quantity. Now coming to my third hint. Third hint was whenever I have minus infinity, what I'll have to do, I'll have to keep my e positive. I'll have to keep my e positive, so that this limit, when the variable takes the limit, it will become e power minus infinity, which will move towards 0. So what I am going to do is minus infinity to 0, I am going to take e positive. So when I take tau to be positive tau outside, this will become minus of minus plus 4 minus I omega times tau. So 4 tau minus I omega tau into d tau. Now for the second case, whenever you have the limit to be positive infinity, take a negative sign outside, so that e power minus infinity turns out as 0. So in my second zone, what I am going to do is I am going to take minus tau outside, so this becomes 4, minus of minus will become plus I omega times d tau, in which case on integration you have e power tau 4 minus I omega divided by 4 minus I omega, the constant, applied between the limits 0 and minus infinity. For the second term, e power minus tau into 4 plus I omega, the constant to be divided is minus sign of 4 plus I omega, which has to be applied between the limits from 0 to infinity. Now we need to keep in mind what is e to the power of tau. Tau taking the value minus infinity will vanish because e power minus infinity is 0. Now when you have minus infinity, tau taking the value infinity, this will vanish, so because e power minus infinity is 0. So only the portion with 0 over here and 0 over here will be left out. And what do we know about e to the power of 0? E power 0 will be equal to 1. So upper limit will be 1 divided by 4 minus I omega for my first term, and for the second term upper limit minus the lower limit, minus of minus will become plus, so this will become plus 1 divided by 4 plus I omega. So this is going to be my second term. So now let me take the LCM, which is going to be 4 minus I omega into 4 plus I omega. So cross multiplying 4 plus I omega plus 4 minus I omega, plus I and minus I cancels off. 4 plus 4 makes it as 8 divided by. Now this is of the format a minus b into a plus b, which can be written as a square minus b square. So this becomes 4 square minus I omega the whole square. So 4 square is 16 minus I square omega square. What do we know about I square? I square is minus 1, minus of minus makes it as plus. So 16 plus omega square. So this becomes 16 plus omega square. So I have got the value for my s x of omega. That is going to be my step number 4. Step number 5, put everything back in your formula required. So what do I have? My step number 5 is going to be syy of omega, which is modulus of h of omega the whole square into sxx of omega. The answer for h of omega the whole square was from our step number 4, which was obtained as step number 3, which was obtained as 4 divided by 49 plus omega square. So replace it over here, 4 divided by 49 plus omega square. And this part sxx of omega, what we had was 8 divided by 16 plus omega square. 8 divided by 16 plus omega square. Now multiplying 8 fours are 32 by 49 plus omega square, and 16 plus omega square makes it as the output power spectral density syy of omega. That's it. Thank you.